Okay, so we start. So today I want to discuss the linear discriminant analysis and also the quadratic discriminant analysis that is slightly more complicated than LDA, and also the nearest neighborhood methods. And then that we compare the difference. I mean that we compare the logistic regression, the LDA, QDA, and the KNN. So models have different strengths. So in which case which model should be used, we will discuss it. And probably we cannot do computer implementation today. So the next Tuesday that we will do computer implementation, R implementation of LDA, QDA, logistic regression, and the KNN with some stock market data. Okay. Do you have any questions from the last lecture or quizzes? Yeah, actually, I think the Antarang let me know that one quiz has some error, so there is only one choice. Thank you. And after that, I corrected. So if you haven't taken it, then you have to answer it. If you have already done, maybe you got 1 point automatically. Okay. Okay. So quizzes are all original. So let me know if there are some errors. So usually, the quizzes are also used last year. So, and 2 years ago, possibly some quizzes. So not many errors remain, but sometimes we have errors. Okay. Okay. So now that I share the screen. And since this is a statistics class, that I would like to discuss the models in detail rather than just doing computer implementation. Oh, sorry. I think we have to. Yeah, chapter 4. So last time that we studied the linear discriminant analysis. So linear discriminant analysis, basically, we use linear boundary to separate the groups. So in some sense, the idea is similar to logistic regression in the sense that boundary is linear. But the original idea is different. So original idea is if we have multiple class, that we consider the distribution of each class in terms of predictors. So for example, if weight and height are predictors, then we use the weight distribution and height distribution, actually the joint distribution of weight and height to differentiate the two groups. For example, maybe football players and mathematicians may be different in terms of weight and possibly height also. So we use that. So, and if we have two distribution, so maybe the blue one is the distribution of one class. So the x-axis is the predictor, and the red one is the distribution of another class. Then we compare the ratio of these heights to see which class this observation. I mean, if x0 is given, if x value is given as x0, then what is the probability that observation belongs to y is equal to 0 or y is equal to 1. So this can be done for multiple classes. If we have 3 distributions, then maybe it's a little clouded if we only have 1 predictors and 3 distributions, but like this. Yeah, so here I made the blue distribution and red distribution, which have the same shape but the different height, and this is intentional. So sometimes the group y is equal to 1 has more observations than y is equal to 0. For example, some mammals, maybe very small percentage of individuals is male and the others are female. So in such a case, the one group has, without any information, the higher chance that to be observed. So red one has more observations, so I make the histogram larger. I mean the area under the histogram larger. So the point is that to compare the height of these two. If we have two predictors, x1 and x2, we can describe it in a plane, and we have different groups and we have the different contours. We will discuss it later. So basically, the given group that we can calculate the probability that the y is equal to 0 or y is equal to 1 or y is equal to 2 or so on. So in this example, you can see the height ratio is the 2 to 8. So we can say that the observation is y. I mean, the probability of y is equal to 0 is equal to 80%. And y is equal to 1 is 20%. In general, we can use the Bayes rule to determine that probability. Yeah, last time that we did this. So suppose that we have two classes, maybe 3 classes are better. Maybe we have 3 classes. So the y is equal to maybe 1 and 2 and 3. Then we have prior probability. So pi, I mean, this maybe k and pi k. So pi k maybe the one with, the maybe 0.1 probability and a 0.2 and a 0.7. Then we have the distribution function. So given k, the distribution of something. So the given k, the distribution of some predictor. Then the predictor value are different. Maybe this is, I don't know, maybe this is maybe 2 and this is maybe 1 and this is maybe 1/2 or something like that. So 2, 1, 1/2, maybe it's maybe 2, 1.5 and 1.5, 0.5. Okay. So that means if we have a figure, distribution. Okay, so x0 value is around here. Okay, x0, 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 and the distribution. So the height is 2, 1.5. So maybe the first distribution looks like maybe looks like this, and this height is 2. But the second distribution may be like this. So this height is 1.5. And again, x0 is here. And this distribution may be like this. So height is very low. So 0.5. Okay. All density curve. So PDF of this. So in this case, okay, so without prior probability, without information of prior probability, maybe y is equal to 1 is most likely. So we don't have any information about, if we don't have any prior information about which class is more likely, then we just choose y is equal to 1 is most likely. But this is the Bayes rule. So the prior probability affects, and the final formula is this. So pi k fk over the summation of the pi l fl. So that is the way to calculate it. So we can see that the probability of y is equal to 1 given this x value is equal to 0.1 times 2 over the summation of the 3 terms. So 0.1 times 2 plus 0.2 times 1.5 plus 0.7 times 0.5. So actually, this probability is not very high. So this is 0.2 over the 0.2 plus 0.1, 0.3 plus 0.35, right? So this is 0.2 over 0.85. So this is probably about 20, maybe 3% or yeah. You can 0.2 divided by 0.85. So this is 0.235. So 0.235. And actually, in this case, basically the product matters. So y is equal to 3 is more likely. Y is equal to 3 given x naught becomes 0.7 times 0.5 over the same denominator. So that means 0.35 over 0.85. So this is equal to much larger value. This is 0.35 divided by 0.85. So 0.412. So, and we can also calculate probability of y is equal to 2 given x naught. That is 0.3 over 0.85. So actually, this is most likely. Yeah, so last time we discussed the horses and the giraffes and deer. So if you find an animal in Michigan, even if the neck is very long, still you see that is a deer, not a giraffe, because the no giraffes, the wild giraffes live in Michigan. So that is a kind of Bayesian estimation. So we use the prior information that the no giraffes and the most wild mammals are deer among those three groups.
I have a question.
Sure.
So for these f values, like f of k, f of x, so that's not a probability, right?
No, not the probability. So
So
this is a kind of density. I mean, if this x is discrete distribution, that is a probability. But for this case, it's density. Okay, so maybe.
I looked at one of the previous slides and it says, you know, fkx equals probability of this. So that's just, you know,
yeah, that's true. That's true. Yeah, yeah, you're right. So basically, you know, I explained only the discrete case, but the for continuous case, this basically, you know, so this discusses the x. Yeah, so this is the discrete case. And continuous case, that we should use distribution, the density function f of x given y. Okay. So the continuous distribution that we cannot use the probability. For example, what's the probability that the tomorrow's temperature at noon is exactly equal to 30 degrees? Then basically it's 0, right? So the temperature is, you know, a continuous variable, so it cannot be exactly equal to 20 or 30. So we have to think about the probability of temperature between 20 and 30. That may be, you know, 0.4 or 0.5 for 40% or 50%. So we have to use the density function to, you know, materialize that idea. So, but for conditional probability, if we use the density function, the discussion is much more complicated. So basically, I made some trick that we discussed only this discrete case, but the continuous case, basically it works in the same way with density function.
Okay.
Yeah.
Got it. Thank you.
Sure. Yep. And the next one that we have some concrete examples about the linear discriminant analysis. We discuss the one-dimensional X and the two-dimensional X. So one-dimensional X means that we only have one predictor. So the situation is similar to the left. Sorry, some time lag. So similar to the left graph on this page. And the two-dimensional case, X1 and X2 are predictors. So the right-hand side. So this figure is the case. So now that we want to have what's the boundary between two classes? That is one thing to do. And also what's the boundary between these three classes in two-dimensional case? And the both cases, okay, so the left-hand side, the boundary is just 1 point, right? So we have some threshold value. And we identify what's the threshold value. And the right-hand side, it's not clear what's the boundary, but here that we prove the boundary becomes linear. And actually, if you see the proof, the even higher dimensional case, you can see that this is linear. Yeah, so at first, the p is equal to 1. So we consider the normal distribution to fit each distribution of X. So we have X and we have distribution, and we assume this is normal distribution. Okay, so this is f k of X. This follows normal mu k and sigma square. So given the class K distribution of X, for example, predictor X, maybe height or weight, is equal to this. So this is just the normal distribution. So this is the normal density, normal mu K sigma K square. Okay. And LDA assumes that the sigma K does not depend on K. So that is sigma 1 to sigma K is equal to sigma. So that is the basically for simplicity, but also it has practical reasons. Yeah, practical reasons. So the practical reason is that actually, if two normal distribution have different variance, it's really difficult to compare the characteristics of two distribution. So if the two distribution have different variance, the typical situation is like this. One distribution is taller but narrower, like this, normal distribution, class 1, maybe slightly. We have like this, right? And the second distribution, okay, so the black one and second distribution is wider, so but much lower, like this. Okay, so in such a case, okay, so black one has higher average, right? So maybe I would say this is this class 2, and the center is the mu 2, and the first one mu 1. So in this case, the higher value of X indicates the class 2. Sorry, just a moment, just the 20 seconds break. Yeah, so the problem is that okay, so basically, the higher value of X, basically class 2, is more likely. And lower value, the class 1 is more likely. That is basically the information from the center. But this is actually not really true if variance is different, because the class 1 has higher density than class 2 only in this area, right? And actually, from here to here, actually the class 2 has higher density. You can see that if you compare at this point, the black one is above blue one. So basically, maybe from here to here, class 2, and from here to here, I mean, the less than this value, class 2, and more than this value, class 2, and in between, class 1. So this is actually a little problematic classification rule. So when I worked for a bank, I just allow different variance for two groups to actually distinguish the recession and the expansion. And the expansion, that we have higher value of indicators such as the inflation or growth rate or industrial production. And that is true, but actually in recession, those values are small, but the variability is large, very large. Remember that in a financial crisis that we have very, low production or car sales or something. So in such a case, variance gets larger, and if we use normal distribution, we come to the conclusion that if the value is extremely high, then it belongs to recession, actually. So that's a problematic conclusion. So to avoid this kind of complication, it's good to equate two variances. So this is practical reason that the same sigma k benefits the fit of the model. So identification of the model. Yeah, so basically we compare, we fit the normal distribution with the same variance for all groups. So only the difference is the mean. Yeah, then what's the pkx? That is the probability of y is equal to k given x. That is this. So this is the pi k f k of x, right? And the denominator, the summation of that over L is equal to 1 to k. Yeah. Yeah, so this gives the probability for each class. And if we decide which class the observation belongs to, then we can take the largest probability. So typically, if we fit this model, maybe the probability is 0.001 and 0.002 and so on, and 0.2 and 0.75 and 0.01 or so on. So you can just take the largest value. So we can check, suppose that this is the class 1, class 2, class 10 and 11, 12 and so on, then class 11 is most likely. So you can decide the class. So what's the boundary of between two classes? So boundary between two classes. Then so basically the f of k, so the value of f of k is the issue. Pi k. Yeah. Yeah. So for now, that we assume that of course, the sigma square is the same, but also that we just ignore the prior probability pi 1 and pi 2 for now. So these probabilities are the same for now, maybe equal to pi. Then the comparing the density function is just comparing this fk of x. And fk of x, then we can just take the logarithm of both sides. So the fk of x is equal to fl of x. That is equal to log of fk is equal to log of fl. So we consider just the log of this function. So log of fk, that is denoted by delta sub k of x, delta sub k of x. So this is the this quantity plus this quantity. So because this is normal density, so if we use the normal density function in the previous slide, then we can get this and this. And when delta 1 and delta 2 are equal, or delta k and delta l are equal, then you can just equate the delta 1 and the delta 2. Then sigma is the same, so we can cancel this term. So, and this is also the same, so we can cancel this term. So that means the x minus mu1 square is equal to x minus mu2 square. So that means, okay, x square is the same for both sides. So negative 2 times mu1 x plus mu1 square is equal to negative 2 times mu2 x plus mu2 square. So that means the x is equal to actually the mu1 plus mu2 over 2. You can just move this term, for example, to the other side, then 2 times mu1 minus mu2 x. And then we move this term to the left-hand side, then mu1 square minus mu2 square. So we divide by mu1 minus mu2, then we get mu1 plus mu2. So we can get that this is mu1 plus mu2 over 2. So this is the boundary. Yeah, so if we have some constant that we may have slightly different threshold, maybe we have taken logarithm, so that we have the log of pi 1 and the log of pi 2. So in such a case, we have some constant. So maybe the formula is slightly more complicated. Maybe I would, okay, let me see. Log of pi 1, log of pi 2 on both sides. So that means the negative, okay, so 2 times mu1 minus mu2 x is equal to mu1 square plus mu2 square. And the 2 move this to the other term. So the log of mu pi 1 plus log of pi 2. Then we divide mu1 minus mu2 and divide by 2. So x is equal to 2 and mu1 plus mu2 and plus maybe some mu1 minus mu2 negative log of pi 1 plus log of pi 2 or something like that. Yeah, but anyway, so maybe slightly different the one, but you can get the threshold. Yeah, and the LDA, yeah, LDA actually assumes that the pi 1 to pi k are also equal. I'm not sure if I mentioned that somewhere. Pi 1. Yeah, I think I didn't mention it, but the LDA, yeah, I believe pi 1, pi 2. Maybe there's some version that the pi 1, pi k's are differentiated, but basically we have some adjustment term and the result is similar. So in such a case, of course, the center, the threshold is not the midpoint of mu1 and mu2. We need some modification. Yeah, so if the pi 1 and pi 2 are the same, then the distribution is like this. So that this is the threshold. So this is the first class. maybe mu1, pi1, and this is mu1, sorry, mu1, and this point is mu2, and the threshold is mu1 plus mu2 over 2. If pi1 and pi2 are different, then this, maybe if pi2 is larger, then this threshold is towards mu1, mu2, so it's larger. So sorry, the other way around. So if pi2 is larger, then threshold is towards mu1. So more likely, so the second class is more likely. So the data is discrete. So basically we observe these observations, then we fit the data. We fit the curve on the data, then we get this distribution. And this second class, okay, so this is first class, second class, and the second class also that we have the histogram, and we fit the density curve to get this curve. And how to get mu1 and mu2? We use just the sample mean. So that is actually the maximum likelihood estimator for mu1 and mu2. And how to estimate sigma square? This is a little more complicated, but basically we use the pooled standard deviation for sigma. So that means the variance is the estimator for difference between observation and the center. So we add up this for all i's, for all k's. So if y1 is equal to k, then we get this, and I think this should be k is equal to 1 to k. Then we divide by n minus k over 1, because we have parameters. So remember that, okay, so at first the variance formula was the 1 over n minus 1 times I is equal to 1 to capital N, xi minus x bar square, right? But in this case, only one quantity was estimated. So that's why we subtract 1. But here, the mu hat k, we have k is equal to 1 to capital K. So we have estimated k parameters. So the k degrees of freedom has been lost. So that's why that we divide this quantity by n minus k, not n minus 1. So sigma hat is estimated by all deviations. So for all classes k, then we subtract xi minus the mu hat k and take square, then take average. So that is the estimated the sigma square. So pooled variance. And these are so-called unbiased estimators of parameters. So that means the expectation of mu k hat is equal to 0. Sorry, the mu k, and the expectation of the sigma hat square is equal to sigma square. So it has some noise, but on average, this is correct. If we have many data sets, on average, this is correct. Do you have any questions so far? So this computation is very easy. So if we have observations, we can just take average. And the variance slightly more complicated. But anyway, this is just arithmetic formula. So you can do very quickly with computer. So how about the X is higher dimensional case? So when P is equal to 2, we say the normal distribution. We can consider the multivariate normal distribution. And if P is equal to 2, we say bivariate normal distribution. So what's the definition of multivariate normal distribution? So multivariate normal distribution looks like this or this. So this is really the bell-curved, bell-shaped distribution. So we say, one-dimensional normal distribution as the bell curve or bell-shaped, but actually that is not really bell-shaped, right? So the bell is the 3D object. So if we have bivariate normal distribution, it's really the bell-shaped curve, bell-shaped surface, I would say. So center is higher, and it has the bell-shaped or mound-shaped. And there are many. Okay, so one-dimensional case, except for the center mu, we only have one parameter variance. But here, the two-dimensional case, the some distribution is just the same shape with any direction, but the sum distribution have different shapes depending on the direction. So for this direction, basically the width is smaller, but this direction width is larger. So we have the several different ones. And okay, so what's the exact definition of the bivariate normal distribution or multivariate normal density function? So that is given by this. So x minus mu, x minus mu. So this is similar. So univariate case, we have just 1 over 2 pi, the square root, and a sigma, or maybe sigma square absolute value, times exponential of negative of the 2 times sigma square, and x minus mu square, right? So x minus mu square. So this corresponds to x minus mu transpose times x minus mu. So basically it's the same. So this means if multivariate mu is equal to, okay, so mu, maybe mu superscript 1 up to mu superscript p. So this is the mu, maybe parenthesis here. So mu superscript 1 to mu superscript p. So x also is x superscript 1 to x superscript p. We have p-dimensional space. So just we have this difference. So since this is the p-dimensional vector, so we have transpose symbol here. Then the variance term. Variance was scalar for univariate case, but the multivariate case, this basically is the p by p matrix. So in univariate case, mu is equal to this mu, maybe the both are mu, so maybe mu vector. So mu is equal to mu vector. And the sigma square is equal to basically, sorry, what should I say? So multivariate, so univariate case is special case. So mu is equal to just mu, and the sigma is equal to the sigma square. Yeah. But the multivariate case that we have the general sigma inverse. So for example, the bivariate case, the sigma may be such as the 1 and 4 and maybe negative 0.5, negative 0.5 or something like that. So this is symmetric matrix. So we have the 3 parameters here. So this is positive definite matrix, the symmetric matrix. Yeah, and LDA assumes that these sigmas are the same. So mu1 to mu k are different. So the groups have different centers, but the sigma are the same. So that means if we make a graph, then so like this situation, So these 3 graphs have the same, the contour plots of these 3 groups are the same, have the same shape. So that is our assumption. So sometimes we have the contour plot equal to ellipse. Like this, but in such a case, another group also have the same shape of contour plot. So the same ellipse with the same direction. So it's not allowed to have this kind of contour plot because the direction is different, or we are not allowed this kind of thing because the shapes are different. Okay. Same shape. Yeah, so this is our assumption. So suppose that for now that we have the pi1, pi2, pi k, those are all the same number. And okay, so at first we think about, okay, so generally that we think about the log of the f sub k of x as delta kx, then we can write this delta k of x in the same way as the univariate case. That we have just multivariate case, we have sigma inverse and the x are the p-dimensional vectors, but anyway, so it's similar. So when delta k is equal to delta L, we consider this. And actually this becomes linear. So, okay, so we compare this for k and L. Then the first term actually that does not depends on k. So it cancels if we equate to delta k and delta L. So only important terms are the last two terms. And the constant term also does not matter. Yeah, so in such a case, what's happening here? What's the boundary? Then you can see that this is linear equation. So linear function of x, right? Maybe linear function of x. X may be multivariate, so x may be like x1 and x2, but anyway, a linear function, linear combination of x1 and x2. And this one also linear combination of x1 and x2. And these two terms do not involve x. So that means that entirely, so this is a linear function of x. So whatever mu1 is, whatever mu k and mu l are, and whatever sigma is, this is a linear function of x1 and x2 in this case. Okay. So we can see that the decision boundary is linear. And if we have pi1 and pi2, we have some constant terms, but that does not really affect the shape of the curve. So if we have, okay, so actually this is regarded as constant. Maybe we have this one, so the log of pi k we have. So we have log of pi k and the log of pi l here. But anyways, these are constant. So this is still a linear equation of x. So that is why the decision boundary for LDA is linear. And basically, it comes from the assumption of normality and also the constant sigma. So sigma does not depend on k. Any questions? Yeah, so basically for observations, if we have observations such as this and this and this, then we can estimate the distribution for each group. Distribution for each group, and we estimate that these contours. Then we can decide the boundary. So here, so at first, the left one is the correct decision boundary in the dashed line, the true, yeah. Yeah, and the estimated boundary is black. So if we estimate this contour, so this is maybe F1 and this is F2 and this is F3, then we can make the boundary. So the solid line is estimated boundary. So this is true boundary. This is true boundary. So in this case, true boundary is the straight line. So the LDA works well. And actually we can see estimated boundary by LDA is similar to the true boundary. But if true boundary is not linear, of course, the estimation is more difficult. But we can see that with only about 60 observations, the estimated boundary is reasonably similar to true boundary. Yeah. So this is how linear discriminant analysis work. So in short, the original idea is to fit the density curve for each class. But based on assumptions that we can say that the boundary is linear. We haven't discussed this idea, but the linear discriminant analysis is better for more than 2 classes. And one reason is that we can compare the all distribution at the same time, so that the boundary between 3 classes are reasonable. So boundary between 3 classes are always like this, Y-shaped in LDA, but the logistic regression may be different, because logistic regression is, if logistic regression is applied for just each pair of classes, it's not multinomial logistic regression, but the simple logistic regression between class 1 and class 2, and class 2 and class 3, and class 3 and class 1, then often the boundary that looks like this. So this is class 1, this is class 2, and okay, so this is maybe 2 versus 3, but also this is 3 versus 1, or something like that. Then what's happening? So the boundary, okay, so you can say that, for example, the class 3, this range is class 3, you can say that. And the class 1, the more than 1, so we can say that the class 1, so this area is class 1. So that is for sure. And this area is class 2. But the other area, it's not clear. 1 rather than 2, but 3 rather than 1. So, but actually the 2 rather than 3. So it's contradictive. So this area, we cannot determine which class it belongs to. So logistic regression. So pairwise comparison is not good for multi-category classification. So not good for more than 3 classes. So even though both are linear, the LDA has advantage for multi-class categorization. Okay, so next, evaluating classification performance. So consider a general problem to measure the classification performance. So suppose that the 10,000 people for 2 classes, the default and the non-default. And the estimated classification rule, the misclassified only 275 of 10,000 the people. So the error rate is 275 over 10,000. So that is only 2.75%. Is it low or not low? And in a common sense, the 2.75% is very small error rate. If you took an exam and your score is 97.25, that's pretty good. But in this case, it really depends on the data. So actually, the default status by logistic regression, I think this is logistic regression. So this is, okay, not that great. So this is the true default class. Sometimes it's called gold standard. So this is the true label. And this is the predicted label. So in fact, we have 303 people in default, and 9,667 people not in default. And predicted classes are, okay, so here. So we can say, that this group and this group are classified correctly because both no or both yes. So you can say 9,750 are classified correctly, but it's not really that good. For example, yeah, for example, so this class, maybe we can focus on this group. The true default status is yes. Within this group, actually 252 were classified as not in default. So basically that we couldn't evaluate the risk for these people. And only 81 out of 333 is classified as default, in default. So out of 333, we only got 81 correct answers. So it's not that good. So we have several measures to evaluate the classification performance, especially if these two numbers, the true default status and are not the balanced, so not 50-50, then the error rate is sometimes the misleading. So you think about the the quiz, the exam with only yes no questions, and that 97% are yes. Then without understanding any questions, you can answer just yes, 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 yes. Then you can get 97. Okay. If you randomly answer yes, no, no, yes, no, yes, no, then you get only 50%. But if just you answer yes to all questions, you will get 97% on average. So the error rate of 2.75% is not really enough. 1 minus error rate is called accuracy. But this is not really enough. So we need some other measures, the more detailed measures. And before defining it, then we have some notations. And here that you have to be careful that this table has been transposed. So the true class is here and the predicted class is here. Probably this is more for common format. And the true class is negative, then predicted class is either negative or positive. If negative, it's correct. So we say the true negative. I would say correct negative, but the true negative we say usually. That is TN, true negative. If predicted class is, the true class is negative, but predicted as positive, then we say this is the false positive because the test result is positive, but it's false. And total is N, so negative. And the true class is positive, but the predicted class is negative, then this is a mistake. So we say false negative. And if positive, actually it's correct. So we say true positive, TP. Then total is positive. Also, that we can say the total of predicted as negative as the N star, the number of observation for predicted negative is N asterisk, and predicted positive is P asterisk. Then we define the sensitivity and specificity. Sensitivity is out of this true class is positive. Okay, so this one. How many percentage are diagnosed correctly? So this one, right? So this is sensitivity. So true positive over P. And specificity is for the negative group. So what if the truth is negative? Then, so how many of them are classified correctly. So true negative. So true negative over the entire n. That is called specificity. So if we have many people, 10 million people, and 1 million people have COVID, and we have the test, and for 1 million, COVID people, if we got, for example, 60% positive result, then sensitivity is 60%. We miss 40% of COVID people in the test. And on the other hand, the 9 million, remaining 9 million, the benign people, and we still diagnosed 1 million people as positive, then specificity is 8/9, because the 1 million that we diagnosed as positive incorrectly. Type 1 error is 1 minus specificity. So that is the true negative, the truth is negative, but we diagnose it as positive. And type 2 error is the false negative rate. So that is 1 minus sensitivity. So the probability that we miss the positive, we miss the malignant patient, basically. And all the, there are many other statistics, such as, Tn over n cap n asterisk, or Tp over p asterisk, and other things. So yeah, we have many other measures, but these are the most popular ones. And here is the example. So this is truth, and this is predicted. You can see. So what's the sensitivity? So if truth is in default, we see 81 people out of these 333 people are diagnosed as positive. So 81 over 333 is the correct proportion. I mean, the rate for the correct diagnosis. So 81 over 333 is sensitivity. So this is only maybe 24% or so. And specificity, so if not in default, how many people are diagnosed as not in default? The 9,644. So specificity is pretty high. Now 9,644 over 9,667. So this is more than 99%, maybe 99.7%. And type 1 error, the other way around. So this is maybe only 0.3%, and the type 2 error maybe 75%. One quiz similar to this. Any questions? So sensitivity and specificity are widely used in diagnostic medicine. Type 1 error and type 2 error are more, statistical terms. And next, the more comprehensive measure for the fit of the model for binary classification problem. So, okay, so how we made this table, we haven't discussed it, but in logistic regression, they usually, if predicted probability is more than 0.5, we diagnosed as positive, or in default in this case. So 0.5 is the threshold, but that isn't always the appropriate threshold. For example, you are lending money to consumers, and suppose one guy has 40% default probability, so they don't return money with 40% probability. Do you lend money to him? Probably not. It's too risky. So the threshold should be lower. So it's possible that we get a different threshold to make a model. This result is problematic because if the consumers are in default, basically the banks make loss. So we would like to avoid it, but actually we miss many of them. We miss 252. We want to decrease this number for better management. Okay. Then maybe we can have more stricter policy about the default status. If balance is slightly higher than normal, then we say, okay, so it's risky. So that person maybe will be in default, perhaps. So we make the difference threshold. Then the table becomes this. So maybe bank concerns about this group, but it gets much smaller. The previous one that we have 250, but now only 138. So basically that we have the lower probability as a threshold. So because of that we have more people predicted as default. So we have 430 here, and before we have only 104. Okay, so 104 becomes 430. Yeah. So in this case, we can also calculate the sensitivity and the specificity. So for example, what's the sensitivity? We have 333 people in default, and we diagnosed 195 as positive. So it's much higher, so 0.6. Originally, it was 0.25. And specificity. Remember that originally this was 99.7%, very high, 0.997. And here, what's the specificity? Specificity is for this group, so 235, sorry, the other way around. So 9,432 over 9,667. So we miss 230, so it's about maybe 0.975. So actually it gets worse. 99.7 becomes 0.975 and 0.25 becomes 0.6. So if sensitivity is important, then this makes much more sense. But if specificity is really important, then actually this may be worse. So we think about the pair of sensitivity and specificity. We have trade-off between these two values, right? So we basically have sensitivity on y-axis and 1 minus specificity on x-axis. So basically, the perfect case, ideal case, is sensitivity is 1 and specificity is 1. So that means here, the 0, 1. So this is the ideal point. And depending on the threshold, we have different pair of sensitivity and specificity. So sometimes here, so in this point, sensitivity is low, but the specificity is very high. If we go here, sensitivity becomes very high, but specificity gets smaller. Then we can make a curve for this. And the R tried the many possible threshold, probably all possible threshold, because we have the finite sample size. If we have 100 sample, the sample size is 100. If we think about 99 different thresholds, then we have 99 different pair of sensitivity and specificity. So we have this curve. So this curve is called ROC curve, receiver operating curve. Sorry, receiver operating characteristics curve. So maybe I should say ROC curve, ROCC. So if the so if we make just rule randomly, then basically the sensitivity is the positive rate and the specificity is negative rate. So sensitivity and 1 minus specificity becomes the same. So if the entirely random rule. So we expect that ROC curve is always the above random rule. I think theoretically, we cannot say that because, for example, ROC curve based on logistic regression is estimated by likelihood function, maximum likelihood. And this is based on error rate, basically. So we have different criterion. So maybe we can go worse than random rule, but basically almost all the ROC curve are between this diagonal line and this, this shape. Okay. So we can see the area under the ROC curve. I mean, the area within this, the 1 by 1 square. Then we can calculate this area in some way. Okay. So this is called AUC, area under the curve. Maybe in the next page, yeah, AUC. So AUC is almost always between 0.5 and 1. We cannot exceed 1. Possibly 0.499 or something based on some estimation methods, but the 0.5 to 1. So yeah, so larger AUC is better. So just comparing one number, you can see overall performance of the prediction model. So if one AUC is 0.7, the other is 0.6, the probably 0.71 is better. Yeah, so that is the linear discriminant analysis. And sorry, so that is the AUC and receiver operating curve. That can be used for any methods such as LDA or logistic regression or methods we will discuss from now. Any questions about AUC, ROC curves? So our package conveniently calculates the ROC curve and the AUC, so you don't really have to code everything. And yeah, so now QDA, Quadratic Discriminant Analysis. So this is very similar to LDA, but we have less assumptions. So only the difference is the assumption on sigma k. So sigma k is a matrix, the P by P matrix, if the X is P-dimensional. If X is P-dimensional, this is P by P matrix. So this is sigma k, and the sigma k depends on k. That is quadratic discriminant analysis condition. We haven't discussed how to estimate the sigma k, but the sigma k can be calculated as the covariance matrix of observations in group K. And yeah, and everything else is similar to LDA. And what's the boundary for QDA? And actually, this is quadratic curve, so that's why we say this as QDA. So just remember the how we proved the boundary of LDA is linear. Yeah, remember that we solved this equation. So we only have the linear term of X. So that's why this is linear boundary. But the QDA, that we have different sigmas. So sigma sub k, sigma sub k, sigma sub k. So in such a case, okay, so sigma k depends on k. So X squared term does not disappear. So left-hand side, X transpose sigma k inverse X, and the other side, the X transpose the sigma L inverse X. Then if these matrices are different, then we can have X1 square or X2 square. So we have the square terms remain. And we can show that the boundary is hyperbola, so not linear in general. So boundary is more complicated. So that means the model is more flexible. So linear for boundary for LDA, but the hyperbolic boundary for QDA. And there is bias variance trade-off between LDA. Basically, QDA is more flexible because the boundary can have a curvature. But the QDA is more complex than LDA, and we have to estimate much more parameters. Estimation is not difficult, so calculation itself is fine, but the more parameters, basically more complicated and less robust, less stable model. So sigma k, so if p is equal to 3, what happens? The sigma k is equal to 3 by 3 matrix. So the sigma 1 1 square, sigma 2 2 square, sigma 2 2 square, sigma 3 3 square. Maybe I also need k here, right? K. And also sigma 1 2 k and sigma 1 3 k and sigma 2 3 k. So this is symmetric matrix. So we have 6 parameters here. And suppose we have 10 classes, k is equal to 10. Then how many parameters? We have so many. So mu k is equal to mu 1k, mu 2k, mu 3k. So we have 3 parameters, and we have 6 parameters for sigma k. So 10 classes, then we have the 3 plus 6 times 10. So 90 parameters. Maybe I should have asked someone. And if this is LDA, how many? LDA, only this, right? So QDA, we have this number of parameters, but the LDA, we have the 3 times 10. Then sigma is just 1 matrix, so plus 6, so 36. But the 3 predictors is really a small case. So if we have more predictors, it's much more complicated for QDA. And I think that we may have trouble to estimate parameters if this number of parameters exceeds the sample size. So LDA is much more stable, simpler model. So here is the performance comparison in LDA and the QDA. And at first, the true curve is purple dashed line. So this is the different simulation. So this is the case that the true boundary is linear. And obviously the green one is estimated by QDA, and the black one is estimated by LDA. So this is LDA, and this green one is QDA. Which is better? You know that the true boundary is purple, so the black one is better probably, because the QDA is unnecessarily complicated model. And the right-hand side, the true boundary is purple line again. So true boundary is quadratic. So then green one is estimated by QDA and black one by LDA again. And which is better? Green one is better probably. For example, you can see that the I don't know. It's hard to see because we only have a few observations. But you can see that, for example, this one is misclassified by linear boundary, but correctly classified by the green boundary. Yeah, here maybe the training performance isn't really much different, but at least the green line is closer to purple line. So we can see in this case, the quadratic discriminant analysis is more accurate. Yeah, so now that we have comparison of these ones, and we don't have enough time, but for today's quiz, we need some information. So just I briefly discuss this. So remember that the LDA and logistic regression have both linear boundaries, although the two have slightly different characteristics. And the quadratic discriminant analysis and the k-nearest neighborhood discussed in chapter 1 or 2, these have the nonlinear boundary. QDA have quadratic hyperbolic boundary, and KNN is more flexible data-oriented boundary. So basically, logistic regression, LDA, simpler, easier, but we cannot deal with complicated situation. KNN and QDA, the more complicated situation we can deal with, but if truth is simple, it may not be good. Okay, so that's it for today. And next time we discuss how to implement LDA, QDA, logistic regression, KNN in R. Okay, so that's it for today. Do you have any questions? Okay, so see you next week.
Thank you. Have a good night. Bye.
Thank you.
You too.
Thank you.